All right, let's talk about an exercise about angle preserving maps, which is actually a true statement, which is nice. Let's see here. There might be a little bit of music in the background. I can hardly hear it, so hopefully it doesn't come up on the recording too much. And if it does, it shouldn't be too big of a deal. And besides, I figure it's best that I get as many videos out as I can because that's sort of been my MO. So, anyways, so we have an angle. We define these matrices, show that t is angle preserving, and if x is non-zero, then the angle between x and tx is theta. So, basically, what t is, and I might call it t theta. So let t theta equal cosine theta minus sine theta down here, then sine theta cosine theta. So what we're going to find is that this matrix corresponds to a linear map which rotates a vector around the origin by the angle theta. So if you start with the vector if you start with the vector 1, 0, then t theta of 1, 0 will just be what you get when you take the vector 1, 0 and rotate it by theta. And so like in R2, that will just be, right, because this is in R2, so it'll be like, it would correspond to the point e to the I pi theta on the complex plane. But anyways, so let's prove some things about t theta. We want t to be angle preserving, which means it needs to be 1 to 1 and, well, preserves angle, meaning the angle between x and x is the same as the angle between tx and tx. No, the angle between x and y is the same as the angle between tx and ty. And by the way, if once we prove that t theta is rotation by theta, then of course it should be the case that the angle between x and tx is theta, because tx is just x rotated by theta. Okay? So anyways, we want to prove that t theta is 1 to 1, and what we're going to do is we're going to actually prove something stronger. We're going to prove that t is a bijection. So the way that we prove this is, let's suppose we take t theta and multiply by t minus theta. So this is going to be cosine theta minus sine theta, cosine theta. Then the next matrix is going to be cosine of minus theta minus sine of minus theta, sine of minus theta, and cosine of minus theta. Okay, and so what happens to this matrix on the right? Well, for the matrix on the right, we have a lot of nice facts about trigonometric functions that we can use, namely that let's see here, cosine is an even function and sine is an odd function, meaning cosine of negative theta is the same as cosine of theta. And that sort of makes sense because cosine of theta is 1, and then if you go to the right, you go down to negative 1 and then up to 1 and so on and so forth. And if you go to the left, you go down to minus 1 and then up to 1 and so on and so forth. So you can kind of use an argument like that to convince or remind yourself that cosine of minus theta equals cosine of theta. And then as for sine, sine of minus theta is minus sine of theta. So if we take minus sine of minus theta, that's going to be just positive sine of theta. Then of course we have minus sine theta up here, and we have cosine of theta here. Alright, so let's multiply these out and see what we get. So at this point, I'm actually, I'm going to replace cosine of theta with c, and sine of theta with s, just for shorthand, because I'm lazy and I don't want to write out all of the things out, because we're going to be writing sine and cosine of theta a lot. So anyways, we get cosine squared plus sine squared in the first coordinate, and then we get, so here in the next one we get minus sine cosine plus sine cosine. Then on the next row we get minus sine cosine plus sine cosine again, and then we get minus sine of theta squared, which is going to be positive sine squared of theta plus cosine squared. Okay, but this is sine squared plus cosine squared is 1, and then the other entries are 0. And then if we do it the other way, then here, so we're going to have cosine, sine, minus sine, cosine, cosine minus sine, sine, cosine. Because I've literally just taken the thing from before and flipped the two matrices. Alright, so now when we multiply this out, we get cosine squared plus the quantity minus sine squared squared, which is just positive sine squared. And then we get sine cosine minus sine cosine, sine cosine minus sine cosine, and then sine squared plus cosine squared. So again, this is 1, 0, 0, 1. So thus, t theta is invertible, and so t theta is bijective, and so t theta is 1 to 1, because a bijection is a map which is both 1 to 1 and onto, and this is a bijection, so it's also 1 to 1. Alright, so got that out of the way. The next thing we need to do is we need to prove that it is angle preserving. So let's see here. Alright, so what we're going to do is we're just going to suppose we have x and y as vectors in R2, then what we want to prove is that the inner product of tx and ty is the same as the inner product of x and y. So tx comma ty, take this inner product. This is going to be, let's see here, so t cosine minus sine, sine cosine, and then x is going to be just x1, x2. In general, this is what general elements x look like. And we have another cosine minus sine, sine cosine, and then y1, y2. Okay, and so then what? Should probably do this on the next line. So we get x1 cosine, let's see, so this is a vector. x1 cosine plus x2 sine. Then we have minus x1 sine plus x2 cosine. And then we have y1 cosine plus y2 sine. And we have minus y1 sine plus y2 cosine. And then just by the definition of an inner product, this is going to be, let's see here, so we take x1c plus x2s times y1c plus y2s, and then we add the other one, c minus y1s plus y2c, and then we FOIL these out. Okay, so we get x1 x1, y1, c squared plus x1, y2, sc plus x2, y1, sc plus x2, y2, s squared, and then I'll continue on the other line, on the next line, to FOIL the next term. So we get a plus x1, y1 sine squared minus x1, y2 sine cosine minus x2, y1 sine cosine plus x2, y2 cosine squared. Alright, and then let's see here. So we've got, let's look at what terms we have. We have plus y1 or x1, y2 sine cosine. This will cancel with this. This will cancel with this. And then cosine squared plus sine squared is 1 again. So we got x1, y1. We can factor out an x1, y1 from cosine squared plus sine squared. And so we'll just end up with x1, y1 plus x2, y2, which is precisely x, the inner product of x and y. Hence, t is wait a minute, angle preserving. This is inner product preserving. Hence t is inner, oh wait. Yeah, we're not done yet. We might be able to use a previous exercise to conclude from this something. We might be able to get, we might be able to use previous exercises here, but I'm just going to do all the work because it's not too much. Okay, so next, let's look at the norm of Tx. So this is the norm of cosine minus sine, sine cosine, x1, x2. So this is the norm of x1 cosine plus x2 sine minus x1 sine plus x2 cosine. Let's make this a little neater. x1 sine plus x2 cosine. Okay, and so then this is going to be the square root of x1 cosine plus x2 sine, this thing squared, plus minus s1 sine plus x2 cosine, this thing squared, 1/2 on the outside. Alright, and so now what? This is going to be, we just FOIL it again, x1 squared cosine squared, plus, then we'll get two factors of x1, x2 sine cosine, plus x2 squared sine squared. Then we'll get a plus x1 squared sine squared, and we'll subtract two factors of x1, x2 sine cosine, plus x2 squared sine, no, cosine squared. Again, we have a 1/2. This cancels with this. And then x1 squared cosine squared plus x1 squared sine squared will just be x1 squared, because sine squared plus cosine squared is 1. And then we get, so this plus x2 squared 1/2. And again, this is the norm of x. Alright, and so what can we do with this? So finally, let's look at the angle between Tx and Ty. This is arc cosine of Tx, Ty divided by the norm of Tx times the norm of ty. And this is cosine inverse of, okay, so tx, the inner product of tx and ty is the same as the inner product of x and y. The inner product of the norm of tx is the same as the norm of x. The norm of ty is the same as the norm of y. And this is precisely the inner product of x and y. Hence, T is angle preserving, because we've proven that it's 1-to-1 and in fact it's a bijection, and furthermore it preserves angles. The angle between tx and ty is the angle between x and y. Next, suppose x is non-zero. We want to prove that the angle between x and tx is theta. It's here. So then, the norm of tx equals the norm of x, which is not 0 because x is not the 0 vector. So, tx is not the 0 vector. So, we can do some calculations with this fact. So we can compute the angle between x and tx. So this is the angle, what am I doing? This is the inner product of x and tx. I don't know why I wrote the angle. We're not quite there yet. We're almost there. The inner product of x and tx is, so we have x1, x2. So this should say also, so this is the inner product of this with x1 cosine plus x2 sine minus x1 sine plus x2 cosine. So this is x1 times x1 cosine plus x2 sine plus x2 times minus x1. So yeah, this exercise, there's a lot of calculations that you end up doing. And I feel like there's a lot of this type of thing when you're dealing with trigonometry. You get a lot of results that, like the results themselves are really nice when you interpret them geometrically, but a lot of times they can involve a lot of computations. But anyway, so these two things will cancel out, and we're left with, we factor out a cosine, and we get cosine times x1 squared plus x2 squared, but this is just the norm of x squared. All right. Therefore, we can compute the angle between x and tx. So it's arc cosine of x, inner product of x and tx, over the norm of, let's do this, for the norm of x times the norm of tx. So this is arc cosine. So on top, we've got this inner product, which we just computed, is the norm of x squared times c, which is cosine of theta. Then on the bottom, we've got the norm of x times the norm of tx, but we've proven that the norm of tx is the same as the norm of x. And so all the norm of x's cancel, and so we get arc cosine of theta. But this is exactly theta. And that's what we wanted to prove. And so now we're done with the exercise.